My name is Waris Sagheer, and I manage the Cisco transport for 5G services. So what I will talk about today is give you an overview what are 5G transport requirement. Then I will talk about Cisco 5G xHaul transport vision and strategy. Then I will talk about Cisco Solution in detail. Lastly, I will touch base upon the customer case studies which have adopted those solutions. So in terms of one of these business landscape, and this slide you may have seen yesterday, but here is a key point. In terms of transport, ARPUs are flat, and there is a pressure on mobile operators to go beyond consumer services. When they use the term consumer services, they're actually talking about mostly video traffic from 55% to probably 75%. And I had the opportunity to talk to most of the operators around the world. All of them have the same traffic. And this traffic is Netflix, YouTube, depending on where you are. Okay? Now, video is great. It doesn't make money. So the focus is, okay, let's shift to the vertically targeted services, transport, utilities, and let's see if they can help with the mobile operator business growth. That's one of the hopes of 5G. Okay? Now, there's another trend. If you look at LTE, which has done a fantastic job of connectivity. So one of the promises of 5G will be about immersive experience. When I use the term immersive experience, it refers to low latency requirements for quality of experience. That's another requirement in the network. Okay? Now, let's look at 5G definition of major use cases and what do they need from the transport side. You may have all heard about enhanced mobile broadband. Right? EMBB is basically including fixed wireless access. Okay? This is like the broadband, and Verizon Wireless has launched the service. They are offering 300 megabit today, which can go up to 1 gigabit in their fixed wireless access. This has been launched in last October. What is the requirement from enhanced mobile broadband? Increase bandwidth and capacity. That's number one. Second one, massive machine type communication. This we are talking about massive IoT. What do you need? Scale. Lastly, URLLC, ultra reliable low latency communication. What does it require? Low latency, meaning push data plane to the edge, intelligence in the network. Now there are three separate requirements: bandwidth, scale, latency. Guess what? We have been building networks for many, many years, not for three types of services, for one type of service, basically bandwidth. Bringing these divergent service requirements, that's where you need a programmable and flexible transport. Okay? Now, in terms of services, mostly the EMBB is the major service type, which has been launched in the world. Verizon launched it, AT&T launched it, SKT in Korea, multiple operators have launched it. Apart from EMBB, there is no service which commercially has been launched. However, there are talks about other kind of services. For example, I had a conversation with one of the Japanese operator. They talked about secure remote car software update. So you know all the software, all the cars are pretty much software today. And Tesla in US does this even today. But Tesla has a very closed loop. So let's say the Toyota or Honda, they need to do this. That will be a value-add service. It is not a low latency, but it's a high bandwidth application and a secure application. Another customer, which is one of the counties in US I'm working with, they want to make a slice in the network, a secure slice for mostly police, hospitals, fire brigades, and all the public sector. That's a slice, but they need a secure slice. And then smart city, basically, you may have seen big belly kind of a trash cans, which are smart trash cans, which can, compress and reduce a truck roll. And lastly, augmented reality and virtual reality. This is where it is going to help with the immersive experience. For example, if you are in a stadium and you are sitting at the, pretty top row and you're watching a game, virtual reality can help with that. And there has been trials and work going on across the world. So those are the different use cases which tie up to the higher bucket of use cases from 3GPP I talked about. Now, from timeline perspective, we are in 2019, okay? City level 5G, which I talked about, Verizon Wireless, 4 cities, AT&T, and others have launched the service. These are limited launches. The commercial launches you will be seeing in 2020. Now, if you see the evolved use cases timeline, this is like 2019 and beyond. But on the top, you can see new use cases about URLLC. So this is interesting. The customers, this is where they're worried about. EMBB, we understand the bandwidth. What they have not been ready and been doing in the network is taking care of the latency component. So hence, the operators need to take care of both the requirements. So once you're planning your network today, it has to be programmable and flexible to cater all the 3 requirements: bandwidth, scale, and latency, okay? And this will be kind of a wave 1 EMBB, and the wave 2, you will see the latency coming into the picture. Now, let's go a little bit deeper into the requirements for 5G. Number 1, the radios are evolving. We all know that, okay? 5G NR is coming, and different talks have been talked about. But here is another thing. Many operators which I've talked to are taking the opportunity to even basically add capacity to their LTE networks. They're adding carriers. They're adding sectors. They're adding macro sites. These are LTE networks. Now, add on top of that 5G NR, which will be commercially available, I think, this year, around this May, June timeframe in multiple operators, adding 3.5 GHz, sub 6 gigahertz, or millimeter wave, 29, 28 gigahertz. Licensed and unlicensed carrier aggregation, basically bringing multiple carriers together. It's like adding more lanes, gives you more bandwidth. MIMO, 4T4R is becoming like a baseline, meaning 4 transmit, 4 receive, 64T, 64R. That's massive MIMO. And lastly, HETNET. All these radio enhancements mean one thing from cell base station perspective: higher bandwidth and capacity requirement. So NGMN has done a very good job of documenting this. It's a very good example. I'll give you a quick overview. Today's national average of LTE base stations is 200 megabit per second. National average. So 200 megabit, if you add MIMO, you are looking at around 600 megabit per second, probably, okay? Add 5G NR to it. With all the MIMO, the calculation comes to 8 gigi per base station. And you can see the math in NGMN document. So what does that mean? It means the traffic, your access networks, which were mostly 1 gigi, they need to go to 10 gigi. But if you want future proving, get 25 gigi. So you will need dense 10 gigi and 25 gigi platforms. Number 1, all the radios which will be coming in 5G NR, in the first phase, all of them will have 10 gigi interfaces. And then second phase will have 25 gigi interfaces. Okay, so you need more 10 gigis. Fiber is still a challenge in all over the world. So BiDi optics will be becoming kind of a key requirement. I already have requirement from one of the tier 1 operator. In Europe, they ask specifically 25 gigi BiDi. Okay? Hence, if you have dense 10 gigi and 25 gigi in access, what do you need in pre-aggregation? 100 gigi. And aggregation, dense 100 gigi. What do you need in core? 400 gigi. That's how the bandwidth is translated in the network. Okay?
So when do you expect IP core will require the 400 gig? Is it in 1 year, 2 years, 3 years? What's the expected? Because obviously in the first 2 years, you don't expect.
So the question is, when do we expect this 400 gig coming to the core? I do not expect this to happen in a year time frame or in a half time frame. But in terms of evolution and planning, it may happen in 2 to 3 years from now.
2 to 3 years.
Exactly.
More in the capital space, right?
So when we do more commercial launches, when they become more widespread, you will need it. So by the way, this is very much similar to we saw in when we did the LTE networks design. And by 2013, 2014, it becoming a mainline requirement to do end-to-end IP. Okay? Yes. Sure.
We are saying we'll need 400G in IP core. So we say in a couple of years.
Yes.
At the same time, we are saying that when 5G comes, we are going to distribute our content to the edges or bring the services to the edges. Do you really think the core will be required in that time?
That's a good question. So the question is, when we are offloading, why do we need to bring the 400 gig? Even in that scenario, number one, in all parts of the world, the peering availability is still going to be a challenge. Distributed peering may not be available because distributed peering means all the sites have the peering connectivity. That's one. If it is available, great. Even in that scenario, the bandwidth growth being projected and the applications being talked about, you may require 400 gig. That's why I use the term, the eventual goal would be 100 gig or dense 100 gig may do the job initially, but if the bandwidth growth becomes explosive, because many of these applications we do not know will be coming in, you may require the 400 gig. So it would be good to plan for it today, at least think about this. We are not saying that go and start deploying 400 gig today.
But in that case, will it be IP core or it could be a simple optical core suited?
It will be IP core. Where I see it, and I will talk about this a little bit, IP will be a dominant technology moving forward. This is what we think, and because the flexibility and consistent OEM it brings to the network.
Okay.
Now, let's quickly look at the end-to-end network architecture. So on the bottom, what I mentioned is, what is LTE? Centralized services. North-south traffic, centralized DC, separate wireline and wireless network, okay? Let's talk about 5G. Number one, disaggregation and virtualization of packet core, okay? Meaning control plane, user plane. Disaggregation and virtualization of RAN, which is happening now. You must have heard the announcements from Rakuten and others. Centralized unit, distributed unit. Okay? These are virtualization component and distributed. Number three, if you see the backhaul, which is, all of us know about this, then there is a term called midhaul coming in. Backhaul latencies have been talked about less than 10 milliseconds one way, which is pretty much most of the networks can do today. Midhaul is the network between CU and DU. Latency, less than 1 to 5 milliseconds, okay? Then front haul. Radios are getting packetized. What does that mean? CPRI was TDM. eCPRI, ROE, XRAN, ORAN, all are packetized. They are layer 2 or layer 3. So there's an actual layer 2 or layer 3 frame coming out of radio. Hence, the front haul will evolve from TDM to packet-based front haul. That's an evolution of the network, okay? Now, and that's the reason we call it xHaul, backhaul, midhaul, front haul, okay? And then Sumit talked about distributed peering, talked about the far edge, which we multi-access edge computing. And then, not to forget the end-to-end network slicing, which will be, I'll talk about more in detail. I have a couple of slides on there. Now, what is going to change in 5G? As compared to centralized services, it will be flexible service placement, meaning you should be able to place the services where the SLAs are required. And let me clarify one more thing. When I say flexible service placement, there's also flexible workload infrastructure come into the picture. because many of these are now virtualized component. Rather than just the PNF, there will be VNFs too. So you need to take care of services as well as transport. East and west traffic, this is which will become more dominant because of the placement of caches and peering. Edge DC and edge compute, which is I think Santano talked about it yesterday, probably in detail, what are different places you can place the edge DC. And lastly, converged network, and Sumit touched upon that too. When I use the term convergence, I mean two things. When I talk about wireless, it means 3G, 4G, 5G, all in one, as well as wireline, meaning Ethernet services and business services in the same network. Okay? So that will be dominant, and why? Cost is the number one reason which will drive this. Okay? Now, why do I think end-to-end IP is critical to achieve this vision? IP brings flexible service placement. Well, you can certainly use layer 2 in parts of the network. However, there is what we want to do from network design perspective. Our rule is reduce network touch points, meaning consistent OEM have single technology. It will reduce human errors. Okay? It makes automation much more simpler. Thirdly, slicing will be very much effective using an IP-based slicing rather than using a TDM-based slicing. And security becomes consistent across the network. These are the key reasons we think IP will be a dominant technology in the overall end-to-end network: backhaul, mid-haul, front-haul. Now, let me talk about the vision Cisco has to address those requirements. And Sumit has shown this slide before. I will be focusing on the transport part, which is the second from the left. What is our strategy is build a programmable and massive programmable transport with massive bandwidth portfolio. It has to be converged. Converged meaning should be able to do wireline and wireless together. And I will talk about some of the technologies which will enable that, like 802.1 QBU, like TSN will also help. It is strict priority. Simplicity comes with end-to-end XR. From one RU platform to a chassis-based platform, you will have IOS XR. It will support the scale, resiliency in any topology. It can be hub and spoke, it can be ring, and security from the transport perspective, and should enable flexible service placement. Network slicing should offer differentiated services, and it will enable optimal infrastructure efficiency. Lastly, we are supporting Open vRAN, so openness of RAN with packet-based front haul will be one of our strategy. I will talk about these points in Open vRAN section also. But there's also a financial opportunity. What do I mean by that? The left hand, which says you can use network slicing as a service. And since you have multi-access edge compute, you can use this location to even host enterprise services or immersive application services. The other 2 points, resource utilization and operating efficiencies, these are the save money option. How do you save money? When you do statistical multiplexing, when you do multi-services, you are actually saving money. With operating efficiencies, with simplification, scale, resiliency, you can also be saving the money from operational perspective. So left-hand side, make money. These two right-hand side are basically save money. Okay? So now let's look at what Cisco solution would be. What we are offering is a single converged packet network infrastructure to basically offer fixed and mobile services. The network should be able to scale up to 500,000 routers. We already have a production network in the world with end-to-end Cisco running 250,000 routers. What we want to make sure is across the network, from protocol, from automation, the network should be able to handle that scale. It should be able to support 4G and 5G requirements with the radio splits. It should be able to support all the 3 services I talked about: EMBB, URLLC, and MMTC. Multi-access compute should be able to be integrated in the network fabric, and also soft network slicing should be enabled in the network. Now, from portfolio perspective, and Sumit went into details, here's a requirement. You need dense portfolio. It should be fixed, meaning 1 RU, 2 RU, and it can be a chassis, depending on network location. It should be able to support different form factors, and we are going to support 120 gigi all the way to 3.6 tera. Now, from IP core, ASR 9K and CS5500, aggregation, we have the portfolio pre-aggregation, we have fixed portfolio, chassis-based portfolio, and at the access, we also have a fixed portfolio, all running end-to-end XR. This is ready today. This we are shipping today. So our 5G portfolio from backhaul and midhaul is ready today. Then there's another component, centralized RAN. CRAN is where you bring BBUs together in a central site for operational efficiency and radio gains, okay? Operational efficiency is the primary reason now. We also have a portfolio because you need BBU hotel router and you need low latency switches for things like elastic RAN or Nokia side haul, what they call it. We support both these functions. We have a very good portfolio in terms of NCS 5500, 540s. Now we are also introducing dense 25 gigis to be connected to virtual to compute. So like dense 48, 25 gig interfaces will be coming in the NCS 5500 family. Hence, the BBU hotel router and switching is also covered part of the portfolio. Okay? So both these DRAN and CRANs are covered. From programmable transport perspective, unified underlay, segment routing, and unified overlay service plane based on BGP VPN. That's basically helps with the programmability. Segment routing is programmable, and I will talk about a little bit one more slide later, but segment routing will help with the traffic engineering and the enhancements we have made for slicing, like flex algorithm. Performance management, I will talk about those a little bit later. So what is the value out of segment routing? So it does help with create new revenue. It helps with the deployment of ease, so you can integrate into existing MPLS networks. So let me clarify one thing, guys. I'm not saying that you go to 5G, you have to go and just rip off everything from MPLS and go to segment routing. Nope, that's not the intention. What we are recommending is, with 5G requirements, segment routing is the optimal solution. So that's why we are recommending basically, you have to go through a journey from unified MPLS or MPLS to SR because it offers those flexibility and programmability. So it has and then it monitor health, data path validation, and then availability with automated 50 millisecond convergence in any kind of topology, and also loop-free convergence, all using multi-vendor approach, okay? Now, let me summarize what is our transport technology. Sorry, yeah, go ahead.
With the segment routing, so throughout the sessions and through conversation with Cisco, we've been talking about the slicing around the segment routing capabilities. And you mentioned that, and you also mentioned that there is a revenue-driven capability with segment routing. So whether it's wireless or wireline network, we understand that segment routing can slice. But is there a particular use case that can really help in that revenue-generating stream, with segment routing?
So the one use case I talked about in the beginning, so if you need to, and by the way, we had this demo in the MWC also, for kind of a secure slice you can build with all the, for example, public sector. This is one, like Department of Defense or something which is requires security. You can build a separate slice for that. The counties or states or certain schools, they can have a separate slice. So those are at least the use cases the customers have been talking to me. Other one is a private LTE also. So private LTE is about getting like FedEx or like different enterprises, if they require a specific service, they can do that with that too. So all those will be possible through the slice concept. Okay. So let's look at from the bottom. Segment routing, MPLS, this is one which we are shipping today. With the evolution to segment routing V6, SoftBank is already deploying this. It has been a public announcement. So segment routing MPLS to segment routing V6. Why do we think V6 would be the way to go eventually in the future or in like next few years? The reason being this, SR MPLS can do most of the stuff. However, SRv6 bring the best of IPv6 and SR together with service chaining, virtualization, and lastly, help with the scale and simplicity. So if you, and by the way, if you look at the packet core world closely, there's a 3GPP group working on replacing GTPU with SRv6. Once that happens, it will significantly simplify the network. It's still in works. I don't know when it will happen though, but it will significantly help with the network simplification, okay? Segment routing performance management. So that's another part which is important to understand. Today, we have to do TWAMP or IP SLAs, and then there's a NetScout and different vendor tools out there. You really do not need to have all those out of the network tools to do that. Segment routing performance management will help to do delay, jitter, loss, and OAM, part of the routing protocol itself. This is a feature which is coming in. You will be seeing those basically part of the segment routing deliverable. Hence, single routing protocol will help you deliver that. So think about this. Instead of talking about latency, you can actually calculate exact latency in the link and the network and steer your traffic based on the requirement. That's a real-time latency we're talking about, not the matrix which we put through the routing protocol. And then from clocking perspective, 1588 and Syncy, I will talk about clocking a little bit later across the network, phase and frequency both. On the service part, eVPN and L3 VPN, and then on the service orchestration part, Crosswork and segment routing PCE. So segment routing PCE will help you with the holistic network view. That's what it does. It's a controller sitting on the top and will help with inter-domain routing. From timing and synchronization, phase is already a requirement in LTE Advanced Network. And it will be required in 5G. For 5G TDD radios, it will be a must requirement. From numbers perspective, between the base stations, 3 microsecond. From base station to reference time, plus minus 1.5 microsecond. That's a requirement, okay? And then another interesting evolution. I talked about radio evolution, right? CPRI to eCPRI. What does CPRI have which eCPRI doesn't have? Built-in clocking. CPRI is TDM. It has clocking built in. eCPRI does not have built-in clocking. So you have to provision the clocking if you are doing a front-haul network. You have to take care of phase and frequency. Hence, these requirements, what is the solution? GNSS receiver wherever you can, but you will also need PTP for phase and Syncy for frequency. So that will be a baseline requirement. Why? Remember, GNSS can be jammed with a $100 device. And that can significantly impact the network. And this is one thing which we have been talking about this for quite some time, that you need to look for packet-based clocking across the network as a backup. So in case of disaster, you should be ready to do that. Now, from roadmap, from platform, we have a very strong roadmap in terms of clocking. So G8275.1, which is the best clocking, but it is on path. G8275.2, and then multi-profile support, all is either supported or is committed roadmap. What we are also bringing in is enhanced Syncy, Class C timing, and PRTC-B. So PRTC-B will have a much lower strict error requirement as compared to PRTC-A. So Class C timing, if you have, it helps with the number of nodes. It's plus minus 10 nanoseconds, by the way. That has been standardized by ITUT. Okay, let's talk about deterministic networking. Remember we talked about converged networks? Converged network, to build a converged network, you have enterprise traffic as well as your radio traffic in the same network. How do you make sure that the radio traffic always gets predictable latency and lowest latency in the network? So there is a thing called strict priority, which we have in the network today can do a job. But however, if you have a larger packet sizes in enterprise, it can be 9,000 bytes, that can add the additional latency to the packet. How do you cater that? The way is being defined, you can use TSN 802.1q-BU. Notice I'm not saying just TSN. TSN is a family of protocols. None of the other TSN family 802.1q-BV makes sense. 802.1q-BU, which is called frame preemption, it makes sense and is being defined by 802.1cm by IEEE as profile B. So profile A is a strict priority, profile B is frame preemption. You know what is the best solution? Best solution is a strict priority with frame preemption. And we did the simulation, we did the test, and we've looked at the numbers. It gives you the most consistent and lowest latency possible. However, 802.1q-BU is required on the uplink interfaces, you mean NNI side. It only help with 1 gigi, 10 gigi, and 25 gigi. It will not help at all with 100 gigi interfaces. So if you are having 100 gigi uplinks, you don't need 802.1q-BU. If you're using 25 gigi, 10 gigi would be the best case scenario. We will give you the deterministic number, okay? So that's basically 802.1q-BU, frame preemption would help in that case. Let's talk about slicing. Why do we slice? Customers, some of the operators may have mentioned to me, they already do slice today. Slice is customer traffic isolation, but with simplicity. That's what 3GPP has made it clear. We have the slicing definition for packet core. We have the slicing definition 3GPP for RAN. There is no slicing definition for transport. However, and by the way, I don't know if you have seen this, but NSI is the network slice instance, which is the end-to-end slice instance, and NSSI are the different components. So your packet core is an NSSI, your transport is an NSSI, and your RAN is an NSSI. So these are three NSSI, part of one single NSI. And the three buckets being defined in slicings are EMBB, URLLC, as well as MMTC. You can add other values there using a slice differentiator, but slice type are the three major slices there. So what do we need from transport? So if you look closely to the slice definitions, and by the way, these are detailed documents there are three things we need. I need traffic isolation and differentiated services. Traffic isolation meaning I should be able to use traffic engineering depending on the latency and bandwidth requirement, and differentiated services meaning I should be able to map the 5QI QoS values to my transport QoS values, end to end. Okay, that's the requirement. Number two, you need low latency path. So in case of URLLC, you should be able to take the low latency path. Here's an interesting fact there. Not all the time you need lowest latency, number one. So you may need lowest latency, but many times you need latency bound, meaning a range of latency. I don't need 1 millisecond, but I may need 20 milliseconds. In that scenario, the application should be able to use latency bound also. And lastly, bandwidth optimization. All these three parameters, latency and bandwidth, are coming from the profiles, if you look closely into the orchestration of network slicing. How do we handle this? We made an enhancement in segment routing called Flex algorithm. Flex algorithm can help you build logical network topologies. So basically, you will have three Flex algorithm topologies, which will be EMBB, URLLC, and MMTC. Within them, you will build L3 VPNs, which can be different customers within slice VPN A, VPN B, based on the services which they are doing. Then you will use traffic engineering for traffic steering. You can use the traffic engineering policies to basically differentiate based on QoS. For low latency path, you will use MPLS performance management for both the things. You will actually monitor end-to-end latency, link level latency, and steer the traffic. And bandwidth optimization, we have done Optima, which will have the WAY and SRPC together, and then give you the bandwidth awareness too. That's how you will be defining it. Then the SRPC I talked about, BGP link state will do the topology and latency to the controller, and NSO will do the orchestration. This is the end-to-end picture which you can do. So this is what our solution is for slicing, and we think that will help you to do soft network slicing. We do not think that hard network slicing will work because it basically uses a TDM approach, and you need a statistical multiplexing approach.
So just a question on that.
Yeah, sure.
So with the, so you mentioned about the hard network slicing, because traditionally we have been used to carving out our paths through RSOPTs, whether that's end-to-end or single hops, and for like some of the use cases that you mentioned, like for defense or someone else, we have done that in the past where we carved out a strict path. With the controllers coming in and especially helping out in the inter-domain scenarios to carve out an end-to-end path in that space, has there been any advancements in the PC controller where now the PC controller is responsible not only in the core space or the IP edge space, but also spanning towards the 5G because an end-to-end segment routing. So having a single controller, can potentially put the network at risk. So is there an advancement around having the multi-controllers and then controller of controllers to have that sort of capability?
So the question is, if the answer is SRPC is supposed to do that. It should look across different domains to build the end-to-end path. Now the information is very local. You don't need to leak the information to other domains. And SRPC should have the holistic view of the network to build you an end-to-end path. So it's kind of, you can build multiple depending on the backup and other things, but the SRPC job is to do that. And that's what I meant. By the way, when I use the term hard slicing, I mean flex Ethernet kind of a set, not the RSVPTE, by the way.
The flex algorithm.
Flex E, not flex algorithm.
Flex E.
Flex E is the hard slicing. Okay. All right, so from Open RAN, so Santano and Andrew McCabe have talked about this in detail. So what my message from Open vRAN is, we have the transport component ready to use for VNF as in PNF. And I talked about bringing our fabric architecture to edge, and depending on how big the size is or smaller the size sets. And at the same time, we should be able to basically use EVPN, kind of a active-active or active backup kind of a scenario, or dense platform with 25 gig support to help with connectivity of compute as well as the physical PNF as well as VNF. So from solution perspective, we have a good solution to enable the Open vRAN at the edge side as well as depending on our aggregation side. Okay. Now, from automation perspective, there will be a detailed talk coming up later, but let me give you a high-level overview on this. We want to reduce, without the automation will be kind of the key component of this entire solution. So defining an intent and then reducing the human error through NSO, collection of all the data at a central location, which will reduce the strain. What you are actually doing from business outcome perspective with network health insight and network insight, you are basically reducing mean time to know. The key in problem identification is to know faster, and that's what you're going to reduce the time. Then the second thing which will improve with Situation Manager is mean time to remedy. And then once you have identified the problem, once you have the remedy of the problem, then defining a workflow automation on top of that. And then lastly, you should be doing proactive optimization. That's the whole business model about with the self-healing networks are. You reduce mean time to know, you have reduce the mean time to repair, and then you optimize. Okay? So that's basically is being enabled by the crosswork tools, and there will be a talk coming up in the afternoon. So I will touch base upon a couple of customers. One in US, tier 1. They went for a single converged network. They are doing end-to-end segment routing. They will be going production by the end of this year, 2019. They will be doing BGP VPN on top of that, okay? And they are going for packet-based front haul. They are pushing hard on XRAN. They are pushing hard on the packet-based front haul. And they are also densifying their 4G network at the same time. And then there's another India operator, one of the world's only hexabyte mobile data network. They are end-to-end IP MPLS network, 250,000 nodes, production with automation and complete network there. And the reason we call them 5G ready, because they are end-to-end IP network. Then there's another European operator, which basically came to us. They wanted to improve customer traffic latency. They went for segment routing and BGP VPN. What they would want to do is simplify operations, enable programmability, increase network. Some of the numbers, they basically fast reroute configuration was simplified 80%, and they enable programmability and scalability, which reduced the latency by 50% there. So that significantly helped them to achieve their business goals. Okay? So why Cisco 5G network? Rich services, meaning faster time to revenue. Software-driven, open API, flexible OS on any platform, flexible consumption model. Sumit touched upon those topics. Secure massive scale portfolio. I touched upon most scalable, high bandwidth, end-to-end transport portfolio with SDN driven. Cross-domain automation, transformational operational model. Multi-domain, machine language, AI driven. RAN agnostic. So what our transport is, regardless of the RAN network, our transport will work. So we are purely RAN agnostic. We support all the wireless convergence, 4G, 5G, 3G. We are also big-time supporters of Open vRAN. Some of the work being done in front hall management is done by Mark Grayson. He wrote all the Yang models for the XRAN, or now ORAN, for front hall management. What I have is some documents which we publish. I would recommend or encourage people to go through them. There's a white paper our team wrote on the 5G xHaul transport white paper. We also have a webinar from Light Reading, which we did on this topic. Then we also have a podcast. Simon Sprague's, Dennis Haggerty, they are two team members, both have done a great job doing this. We also have webinar recording. These are all public resources. You can use them. Also, I have put a link for Cisco 5G page, segment routing, Cisco Telco. There's a good security white paper. And also, there's a Compass Metro fabric design. If you go to this link, I think there's a Compass booth there in the World of Solution. It's a very good document to look at all the details, configuration. These are actually validated documents. They are not just PowerPoint, so they're much more than that. So I would highly recommend to look at them. And then if you are still on MPLS, EPN 5.0 and 4.0, detailed testing we did end-to-end with configuration. You can certainly use them for your work. So in summary, to cater the requirement of 5G services, EMBB, URLLC, MMTC, Cisco Converge SDN 5G transport enables high bandwidth, low latency, and scale. Cisco Converge transport is ready today for backhaul and midhaul and CRAN hub sites. Converge, supporting wireline and wireless NEG, is also secure, enables simplified operations, and resilience. Massive bandwidth portfolio, which I talked about, which we are shipping, programmable transport, segment routing, BGP VPN, enable flexible service placement through end-to-end IP and fabric-based cloud RAN. We also support soft network slicing, and also Cisco Converge SDN enabled transport enables more CapEx efficiency, better OpEx utilization, and faster time to service. Thank you for your time. I have 2 minutes for questions.
A couple of quick questions. Any questions for Waris? Thank you, Waris.
Thank you.